Next, we want to look at how to determine the end behavior of a power function. Power functions are functions of the form f of x equals ax to the n power, or a single-term polynomial function. Every power function has a degree, which is the power that x is raised to, that value n, and a leading coefficient. Which is the value a, that number being multiplied out in front. What we need to do is look at both a and n to determine the behavior of our function, the end behavior. So in example 3, we want to identify the degree, leading coefficient, and end behavior of this function below. This function has x to the second power, so it's a second degree function, and the leading coefficient 3 is greater than 0. Since what we have is a second degree polynomial, we have a quadratic function, meaning its graph would be a parabola. And since our leading coefficient, a, is greater than 0, it's opening up. Starting from that vertex, if we trace in the positive x direction, we can see that our function is headed to positive infinity. And starting in that vertex and tracing in the negative x direction, we see that our function is headed to positive infinity as well. So in this case, as x approaches infinity, our function value is headed to infinity. And as x is approaching negative infinity, our function value is still approaching positive infinity. Again, we're getting that just by reading the graph and interpreting some things that we've already discussed. That we're dealing with a quadratic function, and we can use that value for a to determine which way the curve opens. In example 4, we have a quadratic function again, since that highest degree is 2. Our leading coefficient is negative 2, which is less than 0, meaning our parabola will be opening down. Starting from that vertex and tracing in the positive x direction, our function is headed to negative infinity. And as we trace in the opposite direction, again, we're headed to negative infinity. So as x approaches positive infinity, g of x in this case, is headed to negative infinity. And as x approaches negative infinity, g of x approaches negative infinity. So let me go back and change that. We're not saying equal to, we just want an arrow to say it's approaching that. Again, we get that by picturing or reading the behavior of that parabola. But now we want to generalize that to work with a wider variety of functions, or a wider variety of polynomials and power functions with different degrees, is what I should say. So the end behaviors of a power function with an even degree will always be the same. And that's what we have pictured on the left-hand side here. If our degree n is even, then our function will either open up if a is greater than 0, or open down if a is less than 0. So that will be true if our degree is 2, 4, 6, and so on. And then if we have a power function with an odd degree, so 3, 5, 7, 9, and so on, the behavior will always be that they open in opposite directions. So we can see with this function g of x, if n is some odd value, then on one end, our function is headed to positive infinity, the other it's headed to negative infinity. This is the case where a is something greater than 0. If a is less than 0, then this picture just gets flipped. And it's headed to positive infinity on the left, negative infinity on the right. So in examples 5, 6, and 7, we can use that information, those patterns, to identify the end behavior of each of these functions. Function s of x is degree 5 with a leading coefficient of 1, which is greater than 0. Since it's an odd degree, they're headed in opposite directions. So as x approaches positive infinity, s of x is not equal to, but should be approaching positive infinity. And as x approaches negative infinity, s of x is approaching negative infinity. And again, if we look back at the curve that we set up here, starting at the origin 0, 0, if we trace in the positive direction, since our value for a is greater than 0, our curve is heading up, and as we trace in the negative direction, our curve is headed down. And that's where we get these two statements about the end behavior of our function. In example 6, we have a 7th degree polynomial, so still odd, meaning the behaviors are going to be opposite of each other. The leading coefficient is -4, which is less than 0. That means that behavior that we saw in example 5 is just going to be switched. So now, as x approaches infinity, r of x will be approaching negative infinity, and as x approaches negative infinity, r of x will be approaching positive infinity. Then in example 7, we have an 8th degree polynomial with a negative coefficient. Since it's an even degree power function, that means that as x approaches infinity and as x approaches negative infinity, our function t of x will be headed in the same direction. The question is just whether it's headed to positive or negative infinity. Since our value for a is negative, our function is opening down. So t of x will be approaching negative infinity in both directions.